and we can go. Okay, so my goal today is a dance of delta functions, namely manage SGLN. And if we're lucky, we'll have time for a second dance of delta functions, not quite delta. The other one is epsilon symbols. Anyway, this is the SL2 weight system. And there is something really funny that happens when you combine the two. So I really hope we'll get there, though it has nothing to do with knot theory. Okay. So let me start with review. So remember, we had a Lie algebra and a basis x sub a. A goes 1 from D1 to the dimension of the Lie algebra. A representation with a basis E alpha. Alpha goes from 1 to the dimension of the representation. And we needed a few tensors. So the structure constants, FABC, which are XA bracket AXB, inner product XC, the metric, which is the metric of XA and XB, these two tensors together completely determine the metrized Lie algebra. In fact, this one determines the these two tensors together completely determine the metrized Lie algebra. Okay, this one is symmetric and non-degenerate, so it has an inverse which is also symmetric, and let's call it T upper BC. And finally, there is a third array of numbers, the row array, which is for the representation, and it goes XA acts on E alpha is a combination of E betas, and the coefficients are called row A alpha beta. Now, with all of this information, given a diagram, we can associate to it a number in the ground field, and it's absolutely horrible. But it's actually at the end not so bad. Okay? So you'll see. Okay? So for example, so basically what you do is for any inner vertex, you put a copy of the structure constants. For every edge, you put a copy of the inverse metric. And for every vertex on the skeleton, you put a copy of the representation tensor, and then you sum over everything, and every index appears twice, once as an upper index, once as a lower index, so the result is independent of the choice of basis. You get a number. The number you can show, so you get a functional on diagrams, and this functional satisfies anti-symmetry, IHX, and STU. Hence, it's really a functional on calligraphic A. Hence, there is a corresponding knot invariant, though we have said nothing about it yet. Okay? But now what I want is to, show you that this is, horrible as this may... Yeah?
Can you change your camera to the other one? Is your other camera working?
Of course it is, and I just forgot. Wait, did I start the video? Yes, I did. But I just forgot to start the camera. Okay, to switch the cameras on Zoom. Yeah, okay. So I want to show you how to compute it. And it actually comes out, as I said, a nice dance of delta functions. So I want to compute all of this for GLN. The Lie algebra GLN, which is just the Lie algebra of all n by n matrices, with the representation, the most obvious representation, namely the n-dimensional representation, namely the way GLN acts on an n-dimensional vector space, namely each matrix is represented by itself. Okay? So GLN with the so-called defining representation. So here first of all, so I need a basis for GLN, and I need a basis for the defining representations, and I need to play games with them. So first of all, what's a basis for GLN? Well, let's just take Xij to be so GLN is all matrices. I need a basis. So let me take Xij to be the matrix that has 1 in row I and column J, and 0 everywhere else. Okay? In other words, the index which I used to call A, or which I used to denote by Latin, the indices that I used to denote by Latin letters from the beginning of the English alphabet, are actually pairs ij. Every ij is a single index. Okay? So in fact, if you thought that was horrible, now each one of the Latin indices gets doubled. So it's even a bigger summation. Okay, so be it. Now, there are very simple rules for how to compute with these matrices. Namely, so Xij times Xkl is equal to, so I don't know if anybody remembers the rules of matrix multiplication. So basically you know, okay, basically the ith row of the output is determined by, well, no, let me say it differently. To multiply, God, you know, better do it, you know, I don't know how to matrix multiply. You know, let me do it the way I know how to do it. So, the way I know how to do it is you write the two matrices this way, like the second one a little bit on top and to the right of the other, and then the matrix multiplication is like for each entry, you multiply the row, the column above it with the row to its left. Okay, so here if I have I and J, and here the entries are, the 1 is at K and L, the only way I will get a non-zero entry is if I multiply this row, sorry, this column with this row, and then I will get here, you know, in this place, I will get 0 unless the distance from the left is equal to the distance from the top, namely of the 1, namely if J is equal to K. So the result here is delta JK, so the two indices that are near each other are deltaed, and then XIL, the remaining two indices go to the output. Maybe I wasted your time. But anyway, now that you've done this, you can compute the bracket. So the bracket of x, sorry, not lowercase x, the bracket of xij xkl is their product done this way. So it's delta jk xil minus the product if you flip the order, so it's delta inl, delta il x, if you flip the order, you get kj as the output. Okay? Good. So in order to figure out the FABC tensor, I need to know what the metric is. So let's figure out the metric. So what is T of Ij with KL? So by definition, this is the trace of Xij xkl. But now, Ij xkl has a delta jk in it. So it's delta jk, but then it gets multiplied by xil. Xil is the matrix with a 1 in just one place, so the trace will be 1 if that one place is the diagonal, and 0 otherwise. But to be the diagonal, it means on the diagonal it means that I must be equal to L. So delta IL. Okay? Now I need to invert the IJKL matrix. I need to invert this matrix, which is horrible because it's a matrix whose indices are pairs of indices. Okay, so it looks like a terrible thing. Fortunately, the inverse of this matrix is itself, and it's completely trivial to prove. So I claim that Tij is also equal to delta jk delta il, and if you don't believe me, you multiply. So you multiply Tijkl with T. So what's matrix multiplication? Matrix multiplication is the middle index gets repeated and you sum over all possibilities, right? So I mean, what's A, B, I, K? It's sum over A, I, J, B, J, K. So you repeat the middle index and you sum over all possibilities for it. So here, if I want to multiply the inverse, the proposed inverse matrix with the matrix, I have to take the middle index repeated, and the other one should be Mn, should be free, and then I should be summing over all possibilities of KL. So I need to carry out this computation. Let's carry out this computation. I mean, again, it's horrible, but it's trivial horrible. So this is delta, what was it again? Ij delta KL, delta LM delta K.
You want to enter JKIL, right?
Sorry?
In the beginning?
In the beginning?
Right.
Oh,
JKIL.
yeah, thank you for catching me. So it's delta JK delta I, well I wrote IL, LI it's the same, and then LM and KN. And this I should be summing over the repeated indices, so over K and L. But the only way this will give a non-zero contribution is if K is equal to J. So with the summation over K, K is really J. And if K is equal to J, then this delta will contribute 1, and this delta will contribute delta Jn. So this is delta Jn. And likewise, the summation over L, this delta forces L to be equal to I, and then this becomes delta Im. So this is delta Im. So we got that I has to be equal to M, and J has to be equal to N, but that means that this index must be equal to this index, or this pair index must be equal to this pair index, which amounts to saying that we got the identity matrix. Okay? Good. So we found, okay, good. What?
Could you explain that trace again?
The trace. So, okay, this is really equal to, so xij xkl is really equal to delta jk. So this is equal to delta jk xil. The delta jk comes out of the trace, and I need to compute the trace of xil. But the trace of a matrix is the sum of the entries on the diagonal, right? A matrix xij has trace 1 if and only if, and otherwise 0, I mean if and only if I is equal to j, because then the 1 is on the diagonal. So the trace of xil is delta il, and that's what I wrote here. Okay? So, I mean, everything is painful but extremely simple, and soon it will stop being painful. So in fact, by the way, already here, we find a sort of nice thing. So remember that inside the computation, what we had to do was to label each internal edge with a lowercase Latin letter, which now becomes a pair, ij. Okay? So let me adapt the convention that when I want to label an end of an edge with an ij or a kl or whatever it is, the first index will be to the left of the edge when I'm looking from the center. So I sit on the center and I look toward the end, and then the first index will be to the left and the second index will be to the right. So when I write ij like this, this is the pair of indices, first I then j. Okay? And then when I want to likewise annotate the other end, so I want to annotate it with kl, so the k should come on the left and the l should come on the right, again, when I'm looking from the center of the edge. Okay? And this edge corresponds to a copy, I mean, this edge really corresponds to a copy of this. But this we've just evaluated. It's delta jk, delta il. So let me rewrite it, so let me replace it by a pair of edges where but maybe I should be using a different color for, but I'm running out of colors. These are a different type of edges. So this is an edge connecting an I with an L and a K with a J. And this is just a mnemonic. This is just a way of remembering the delta functions. The I gets deltaed with L and the J gets deltaed with K. Good. Having done this, well, or not having done this, I mean, next I need to figure out the structure constants. So I need to find out what is FABC, or more precisely, it's Fij KL MN, and this is the inner product of the bracket of xij with xkl with xmn, but we already have all the information. This is the inner product of delta jk xil minus delta I L X K J, inner product with X M N, and again the rule for the inner product is, well, written here or here. So basically the two inner indices are deltaed and the two outer indices are deltaed. Okay? So this becomes a sum of two things. Delta jk and then I with n, so delta in, delta and then the inner L with m, and minus delta IL and then k with n, delta kn, delta jm. Okay? And if, okay, by the way, this is the worst. Okay? So, but let's interpret this. So, suppose now you have a vertex, and it's labeled A, B, C. So, this really means a vertex labeled wait, did I blunder? So it's labeled, so when I look from the inside of an edge, right, the I should be on the left and the J should be on the right. Okay, so I is here and J is there. Again, left and right are as measured from the middle of an edge, and now we're at the end of an edge. So I should be looking from here, and I is on the left, J is on the right. What?
That's the convention you give above?
Yeah, I think so. It's the exact same convention as above. So the convention I gave was when you look from the middle, I is on the left, J is on the right. I mean, the first index is on the left, the second is on the right. So here, when I look from the middle of the edge is here. Right? It's away from the vertex. So I is on the left, J is on the right. Anyway, likewise, here I have K and L, and here I have M and N. And if I use the new type of edges, I have delta JK, delta IM, delta LM. So basically J with K, L with M, N with I. And that amounts to the picture I, J, K, L, M, N. Minus, and again, this picture is just a mnemonic for the deltas. So the other picture comes out this. So I, J, K, L, M, N. So I with L, it's I with L, K with N, K with N, J with M. Okay? And there is only one computation. I told you the worst is over. There is only one computation remaining. And this is, I have to figure out what is, I have to switch to the representation. So the representation is spanned by E alpha, okay, or that was the generic notation we used, but now it's the n-dimensional representation, and I already have indices that run from 1 to n, namely the I and J and KL, so I may as well use the same type of indices, so the representation gets spanned, so R is equal to the vector space spanned by indices EI, by vectors EI, where EI is, well, the standard basis vector of an n-dimensional vector space. So 1 in position I and 0 elsewhere. Okay? So now I need to compute the representation tensor. So R, or no, let me say differently. I need to compute XA acting on EI and write it as a sum, no, not EI, EK, and write it as a sum of ELs with coefficients, right? So let's do it, except XA, I mean, this becomes a pair of indices, so I have to compute Xij acting on EK, but Xij acting on EK, well, the only contribution is if J is equal to K. Yeah, if J is equal to K. And then the contribution is EI. So this is delta JK EI, which amounts to saying, right, that I want to write this as a sum over L of EL multiplied by something. But this just means that the sum here is delta KL delta IL. So the conclusion is that R Ij KL is equal to delta JK delta IL. And now I have my lovely conventions. So if I wanted it to be green. Right, so if I have K L, then this becomes maybe I'm trying to be too fancy with the colors and it's more than my coordination. So this becomes I, J, K, L, and then J gets paired with K, I gets paired with L, that's what's written here. So this really becomes J, K, I, L. Okay? And now, sorry, I need to add pages. Okay, and now I can finally compute whatever I want. So suppose I want to compute this diagram. Okay, so this diagram becomes, well, each edge gets labeled. So, you'll have I, J, K, L, M, N, I prime, J prime, and so on. And each of each internal edge gets labeled with 4 indices, like 2 on each end, and each external edge gets labeled with 1 index, P, Q, R, S. Okay, but I don't really need to know the names of these indices. I only need to know which one is delta'd, is Kronecker delta'd with which. And I have recipes that tell me how to do it. So the recipes say that the vertex here becomes a difference of two things. This and the other one, which I'll write later. The edge here becomes a pair of edges. This is not a crossing like in knot theory. It's just I don't want the picture is cleaner if I don't make them cross. Okay? Each of the external edges remains an edge, remains a single edge, like the blue edges remain single blue edges, and they are connected in this way. Okay? So this tells you completely how the Kronecker deltas are matched. So whatever variable was written here is matched with here. Whatever variable was written here is also matched with here, and so on. So this is one contribution, and then there is a second contribution which comes from the second contribution for the internal vertex, and it looks like this. This pair, and now this connects with this connects with that, and so on. Okay? But now I actually have to compute. Okay? So overall, how many variables are there? So this is a sum of, let's see, 1, 2, 3, 4, 5 external edges, and 4, 8, 12, 16. So I have to sum over 21 variables running from 1 to n. But fortunately, the 1, 2, 3, 4, 5 variables that are along this cycle are all equal, because they are matched with delta functions. And otherwise they're unconstrained. They can go anywhere between 1 to n. So this cycle just contributes a factor of n. Similarly, the remaining 16 variables, 1, 2, 3, I don't want to. All the 16 variables that appear along the butterfly down at the bottom are matched with each other, are deltaed with each other, so they all have to be equal, and their common value runs from 1 to n, so all of these variables contribute a factor of n. Now, these two summations are independent, so this diagram altogether contributes n, oops, that's a nice way of writing n squared. So this summation contributes n squared. Now, this summation, he has, let's see, how many cycles are here? Also 2. Really? Did I blunder? How many cycles are here?
1 cycle, right?
Wait.
Oh, no, 2. Shit. Oh, yeah, right, 2.
2. One goes like this, and the other one is the remaining green. Oh, so this also contributes n squared. So this whole diagram contributed 0. Actually, that's not what I meant. I wanted to give a more interesting calculation. So let's do a simpler diagram, actually. So let's compute this diagram. So this diagram will contribute this minus that, but this is n cubed, is just one cycle. Sorry, I wasn't careful enough to actually close the thing, so it's not obvious that now it's more obvious that it's one cycle. This is just one cycle. So you get n cubed minus n. So in fact, at the end of the day, the computation is fast and easy. Okay? Well, fast and easy, you know what, let's do one more example. So let's compute a diagram with no internal vertices. So this one. Okay? So you see, I don't even need to do anything, and in fact we've done this already when we computed the weight system of near the weight system of the Conway polynomial. You see, each line gets doubled. So all I have to do is follow these lines one time on the left and one time on the right, and when I come to the externals, I follow them. So I do this. So I got one cycle, and now maybe I'll use another color. So now let's start from here. And I got a second cycle, and let's use blue now, because, well, blue is a bit ambiguous, but fine. And this is the remaining cycle. And I think we've gone through everywhere. So this diagram, the weight is n cubed. If the it really is fast and easy. Okay? If the diagram does have internal vertices, it actually becomes exponentially complicated in the number of internal vertices, because each internal vertex becomes two possibilities. Okay? But it's still much more efficient than running summations from 1 to n, God knows how many indices. Okay. Questions, comments? Okay, so let's do SL2. So So first of all, I don't really want to, hello? Yeah?
So what does GLN correspond to in terms of the weight systems? Is it corresponding to the common polynomial, or
it becomes the weight system of the Humphrey polynomial, which we have not talked about yet. Okay, but okay. So SL2 is the Jones polynomial, by the way. So let's do SL2. So actually, I don't want to do SL2. SL2 is isomorphic. Sorry, I want to do SL2, but I want to use a different name for it. SL2 is isomorphic to SO3. And if you've seen Lie algebras, you know it. Okay? And SO3 is the Lie algebra. It's just three-dimensional Lie algebra. It's the Lie algebra of rotations of R3. And it is generated by three things: x1, x2, and x3, where I'm assuming that the coordinate of R3 are q1, q2, q3. So x1 is rotation about the x2, the 2-3 plane. x2 is rotation about the 3-1 plane. Or, you know what, x1 is rotation around the 1 axis, x2 is rotation around the 2 axis, x3 is rotation around the 3 axis. So you can actually write them as matrices very, very easily. X1 is the matrix that has 1 in position 2, 3. So position 2, 3 is here. And minus 1 opposite to it. And the rest are zeros. X2 is the matrix that has 1 in position 3, 1, so you just go cyclically. So position 3, 1 is here, so there is a 1 here, a 1 opposite to it, and the rest are zeros. And x3 is, so it has 1 in position 1, 2, 1, 2, this is here, 1 and negative 1 opposite to it, and zeros everywhere else. Now, computing the products of these matrices is not so hard. Computing their inner products is also not so hard. Okay, the inner product is again the trace of the product. But I will not. I don't want to go through it again. I mean, it's just the same. I mean, but at the end you get something very, very simple. So f, the structure constants, f, a, b, c, becomes something that also has a name. It's called epsilon a, b, c. And epsilon a, b, c is a standard symbol, and it's called, and it's a totally antisymmetric symbol. So basically it's -1 to the power ABC if ABC is a permutation. So basically if none of the indices is repeated, then this is a permutation. I mean, if you don't take twice the same thing, then this is a permutation, and then you take the sign of the permutation, and then 0 otherwise. And the TAB tensor, well, I actually don't remember. I think there is some scalar factor there. But up to a scalar factor, which will amount to an overall scalar factor at the answer, this is delta AB. Okay? And I should have told you what representation I take. But I will not tell you what representation I'll take, because I will do the opposite of what not invariants care about. Okay? So in fact, I am now going outside of knot theory and playing the same game for its own sake. Okay, I'm playing the game without relationship with knot theory. Namely, I will evaluate diagrams that have no blue skeleton. Okay, so I don't need a representation. I will simply evaluate such diagrams for their own sake. Okay, and without choosing a representation. All the lines are internal lines. Okay? So, so let's try to compute it. Maybe that one was a bit too ambitious. So let's start with a simpler one. Let's compute this diagram. So the fact that these are that the epsilon symbols are non-zero only if the three numbers are different from each other means, so right here I'm going to have a summation over an index I, here I'm going to have a summation over j, here I'm going to have summation over k. A contribution arises, oh wait, sorry, in fact, sorry. Okay, I'm skipping steps. Really, here I'm going to label it A, B, C, A prime, B prime, C prime. That are the rules. I need to label each edge twice. Okay, but the TAB tensor is delta AB. So there is really, so A prime is equal to A, and B prime is equal to B, and C prime is equal to C. So really it's enough to label each edge once. So this is the edge A, this is the B, this is the C. Now, I get a contribution only if A is different than B and is different from C. Okay? So basically I get a contribution only if the labeling is 1, 3, 2, or any other permutation. The contribution of a permutation is its sign measured here times its sign measured here. But it's the sign of the same permutation. Actually, yeah, it's the sign of the same permutation. In fact, not quite. So like, my conventions are to go counterclockwise in the vertices. So this will be the permutation 2, 3, 1. And this will be, if I start here, say, it will be the permutation 2, 1, 3. So in fact, the two vertices contribute opposite signs, but always opposite signs. Okay? So the contribution from any permutation will be -1. So the overall contribution is the number of permutations times -1, which is -6. Okay? And here is a lovely theorem. So, theorem. If a diagram D is green only, so I'm still in the simplified case, no choice of representation, and planar, then like here, all contributions will come with the same sign. So all contributions come with same sign. Okay? And the second point is, well, so what are we counting at the end? So in this case, WSL2, which is the same as WSO3 of this diagram, well, counts the number of edge 3 colorings of the graph. And edge 3 coloring is when you color the edges with 3 colors, and no 2 colors are the same. No 2 edges that meet in a vertex have the same color. So this is really always plus or minus 1, and since all of these contributions come with the same signs, there are no cancellations. So this is simply plus or minus the number of edge 3 colorings of the diagram D. And a well-known theorem from graph theory, maybe, depending on you have to tell me if I should go there or not. But then it will be next time because we're out of time. But a well-known theorem from graph theory says that the number of edge 3 colorings is equal to the number of face 4 colorings. So this is equal to the number, or plus or minus, the number of face 4 colorings of D, which is really the number of colorings of the map defined by the complement of D. Okay? So the number, or plus or minus, the number of the 4 colorings of the map, which is the complementary to D. I'm already 40 seconds late, but I really want to finish the sentence. So I mean, for example, well, you know what? No examples. No examples. But let me tell you that this, together with your homework assignment, becomes a statement about W, which is equivalent to the four-color theorem. So maybe I mean, since I already mentioned it, I really must state that statement next time, just so that just for fun. It has nothing to do with knot theory, and it's also useless for proving the four-color theorem. And I'm 2 minutes late. I should quit. Any questions or comments?
Yeah. So just to verify, I was kind of expecting the weight of the diagram above to be 0 because it's an isolated chord.
No. So first of all, we're in a different world. This is a green-only diagram. And secondly, I never told you that the framing relation holds for Lie algebraic weight systems. In fact, it doesn't. I only checked IHX and I only checked STU, which is equivalent to 4T, and the framing independence relation actually doesn't hold. So we still need some work to make framing independence work to get it to be a knot invariant. Okay? Or maybe it's an invariant of framed knots rather than simple-minded knots. Okay? So no, this is actually not 0. Okay.
Is there, sorry.
Yeah. Chinaya?
Is there a systematic way to show that these weight systems then follow this, give you an ordinate follow this kind of relation we want them to follow?
Sorry, I didn't understand you.
Yeah, sorry, I was saying, is there a systematic way to show that the weight systems we get from these algebras give knot invariants that satisfy this kind of relation we want them to follow to give us the polynomials we expect they give us?
Yes, but that's a different story.
I see.
I mean, I'm not in the position to answer this in detail yet.
I see.
Okay. Good. So I'll quit the video.
Oh, wait, so
Yeah.
why did we get -6? Like, I thought we multiplied the signs of the.
Yeah, but the signs, the way I wrote it, these signs are always opposite to each other, not equal to each other.
Why are they always?
Because when you read counterclockwise, which is my convention, then here you're going to read ACB. Suppose you start at the A. Here you're going to read ACB, and here you're going to read ABC. The sign of ACB and the sign of ABC are always opposite.
Maybe I don't understand what you mean by sign. Like
the sign of a permutation.
Like aren't they? So isn't sign of aren't the sign of those the same?
No, the sign of ABC and the sign of ACB are opposite.
Okay, I'll think about it.
Because they differ by one transposition. You flip B and C.
Okay, that does make sense, but okay, wait.
Yeah. Okay, fine.
Okay.
No, that's fine. So the signs are always opposite, not always the same in this case.
And are you counting the number of permutations to get 6?
Yeah. This 6 is the number of permutations.
Oh, okay.
So, but aren't they one is the inverse of the other one? So shouldn't they have the same sign?
No.
I'm so confused.
Sorry. I'm using, okay, there are 2 notations for permutations. Maybe I should have used a better, maybe I should have used square brackets rather than round brackets. The permutation ABC, by the permutation ABC, I don't mean the cyclic permutation. A goes to B, B goes to C, C goes to A. I mean 1, 2, 3 go to A, B, C.
Oh, I see. Okay, that makes sense.
Okay.
Yeah.
So maybe,
Okay.
yeah, so I should have used, yeah, so, or maybe I should have used no brackets. I mean, really, when I say ABC is a permutation, I mean not using cycle notation, using sort of just, I don't know, what is the other notation called? Okay, so we are way late. I'm turning off the video.